Welcome to solverfy.
We are given a weighted graph, and we are asked to use Prim's algorithm to find a minimum spanning tree for this graph. So the graph we're given is a weighted graph on the edges A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. It's a very detailed graph, and you can find it in exercise 4 of this section. I'm not going to draw the weighted graph here because I think it'll just take too much time. It really isn't going to illustrate anything exceptional that the book wouldn't already tell you. But to use Prim's algorithm, first we are drawing the graph with the vertices of our given weighted graph and with no edges between the vertices. So our first step is what I've already done here. I've drawn the graph with the vertices A through P. The next step is to select one of the vertices as a root. Now I'm just going to say that A will be the root arbitrarily. You could pick another vertex if you wanted to. And now we're going to consider the edges incident to A in the weighted graph. Well, we have that there are two edges incident to A, and that both edges have the same weight, which is 2. And so we can choose either edge. I'm just going to arbitrarily pick edge AB, or I mean edge AD, my mistake. Okay, no, the smallest edges are AB and DE, so I'm going to pick AB, length of 1, or weight of 1, I should say. And in the next step, we have that there's one edge still incident to A, and two edges now incident to B, and the smallest weight of these edges is 1, which belongs to the edge AE, which we saw before. And if we add this edge, we don't cause a circuit. So let's add the edge AE to the graph, also of weight 1. And of the remaining vertices that are incident to A, B, or E, there are multiple vertices that have the minimum weight, which in this case is 2. So let's just arbitrarily choose the edge BC. Now we notice that if we pick the edge BC and we add it, we don't obtain a circuit, so this is a legal move. So we add the edge BC of weight 2. And for the next step, the remaining edges that are now incident to A, B, C, or E, we have the smallest weight, which is 1, belongs to the edge CD. Now if we add the edge CD to the graph, we don't obtain a circuit, so this is a valid move, and we add CD with a weight of 1 to the graph. In the next step, we have with all the remaining edges that are incident to A, B, C, D, or E, the smallest weight of 1 again, this time belongs just to the edge DH. Now if we were to add DH to the graph, we would not obtain a circuit, so this is legal, so we add DH to the graph. Next step, we have the remaining edges that are incident to A, B, C, D, E, or H. The smallest weight, which is 2, belongs to multiple edges. And in fact, this is the same as the smallest weight in the entire remaining graph. Now, the way this is going to work is to speed things up, because this is the smallest weight in the entire remaining graph, we'll add all these edges with weight 2, just as long as we don't cause a circuit. So first let's add the edge EF, which has a weight of 2. You see that this doesn't cause a circuit. Let's add the edge EI, which has a weight of 2, also doesn't cause a circuit. Let's add the edge GH, which does not cause a circuit. Let's add the edge DP. You see that this doesn't cause a circuit either. It's going to be a little bit hard to see though, because it's so far away. Let's add the edge AM. Similarly, it is very far away, but does not cause a circuit if we add it. Let's add the edge MN. So now we're considering the new vertices we've added here. Still have the minimum length of 2. So this, if we add MN, we don't get a circuit. It still has a weight of 2. And if we add NO, well, we have that NO also has a weight of 2, and if we add NO, we don't get a circuit, so we can add it. And let's add LP. So if we add the edge LP, we don't obtain a circuit, so this is a valid move. So now I've added all the edges with a weight of 2, as long as they don't cause a circuit. And we see that of the vertices remaining, we still need to connect vertices J and K. Now we have that the smallest weight of an edge to J is 3, and the smallest weight of an edge to K is also 3. So for each vertex, we're going to choose one of the edges with weight 3. So for example, I'm going to pick IJ, which has weight 3. Now we know that if we add IJ, we don't obtain a circuit. So this is valid. And let's add the edge KL. And if we add the edge KL, we see that we don't obtain a circuit, so this is valid. And so now we have a connected graph. So the algorithm terminates. And so by Prim's algorithm, it follows that this graph is a minimum spanning tree. And it contains the edges AB, AE, AM, BC, CD, DP, DH, EF, EI, and GH, IJ, KL, LP, MN, and NO. And these are all the edges for our answer.